So, for those of you guys just joining us today, although everyone is here. Hi guys, just making sure. Anyone joining to recap back in? You already saw in class us do this example right here. A little bit more fully, both using our oh, he turned off. That's why I was like, wow, can't see anything. Using our calculator and using that Boolean programming language to go ahead and get for only certain x's as far as when we're graphing. But then you're able to see a jump right there. You're able to see as x comes to 2 from below, it's headed one place. As x approaches 2 from above, it's headed another place. If you wanted to, you could totally throw little cars on these lines and be like, hey, it's the path to something. And you can ask yourself, where's the car headed? That y. Where's the car headed? That y. And do the two y's agree? Nope. Nope, nope, nope. Sure. But this guy's headed to the close down in and out. This guy's headed to the open in and out, but whatever. They're both headed to in and outs, but different locations. So are they going to be meeting, converging, headed to the same place? No. The answer is no. Now, guys, we didn't get to spend a lot of time yesterday on these other two DNEs. This one I told you could graph and zoom in, zoom in, zoom in, zoom in. Long story short, in pre-cal or even honors pre-cal, we're not really going to see this one much. Maybe in calculus a bit more. But this one you're not going to see much. I just wanted to say, hey, since we're learning limits, I'm going to show you every way a limit cannot exist. And this is one. You're just not going to see it a lot. So if we do see it, we'll talk about it, but you probably won't even see it. But this one, do you guys notice there are two different answers in the boxes? This one says DNE, and this one says DNE, but I'm going to answer positive infinity. What's the difference? At this little car, where's he headed? Negative infinity. This little car, where is he headed? Positive infinity. So as we go to negative infinity from one side, positive infinity from the other, my question is, do they match? Do they agree? No. So that's a DNE, a DNE, a DNE, a DNE. This one is a DNE because it's like, well, it's not headed to, what's the informal definition say? It's not headed to, wow, that was farther back than I thought. It's not headed to a single number. Is infinity a single number? It's an idea that's ever expanding. True? Okay? It's not a single number. So we would say, okay, it technically does not exist. But even though it technically does not exist because it is not a single number, we're still going to answer because what's true about my two cars? They're going to the same direction, right? They're approaching the same idea, and so we'll answer it with the idea even though it's not a number. And by answering it with infinity, we're saying we realize it's not a single number, but they are agreeing. So what would happen, what do you guys think, if they were both headed down at that A? The answer would have been negative infinity instead, right? But if they don't agree, the limit does not exist, so we're done. Boop, boop. So what would you guys do for this one? We're getting to some properties in just a second, but before some properties, let's talk about this example. That's my function, and this is our objective. That's my function, and this is our objective, to take the limit as x approaches 4. You're allowed to use your graphing calculator for now until section 12.2. What? What's scary? Don't worry, you're fine. Shh. Don't worry, you're fine. Is this a piecewise function? No. Is it a limit? Yeah. Do I need to come from either side? Uh-huh. Could I maybe try to plug in and see the answer? Sure, but if you try to plug in, what's going to happen? Yeah, it's going to be over 0. But remember yesterday how I said something like what's on top can give you a clue as to what's happening in the graph? Wouldn't this be square root of 7 minus 1? Is that a whole? No, because a whole gets a 0 over 0. Removable, the zeros are shared. We can factor. This isn't a whole. There's going to be a vertical asymptote at x equals 4. Can you guys check out the graph for me? Can you guys check out the graph for me? And then I want you to ponder, sketch, check out the graph, sketch the graph, and then ponder. Ooh, well, don't be the graph. Be on either side of the graph and figure out where you're headed. Just be the graph. We need there to be movement. We need there to be approaching, right? Well, but remember, it doesn't have to be there with the table. It's all about the approaching. Wait, why are there tons of errors? There should only be an error at the vertical asymptote. You should be able to approach.
Because there is no vertical.
But what about 3.9? And 3.99? And 3.999? And 4.1, and 4.01, and 4.001. Anybody have the graph? Gracias. If you guys don't remember from the beginning of the year, there's a horizontal asymptote at 0 because the degree of the bottom wins, so I know it's getting closer and closer and closer to 0. No, because the square root makes him like a half-degree power. And then I have my vertical asymptote at 4. Why am I not even going to worry about a table? Why am I not even going to worry about plugging in values? Because I can look at the graph and say, you know what? I can see where he's headed from below, and I can see where he's headed from above. From below, from the left. Where is he headed? Where's the little car on this branch going? Boop, negative infinity. We can answer. It's okay, negative infinity. I know it's a fuzzy answer because it's not a number, but it's okay, negative infinity. How about if I come from above or come from the right branch? Remember 4.1, 4.01, 4, where's it headed? Positive infinity. Do they match? Look at your shoes. They're supposed to. Do they match? No, so therefore the limit as x approaches 4, what's my final answer? Does not. What aren't you getting, Robbie? This picture? Let me see real quick. That's weird. It's only showing like part of it. What mode are you in? You're in function mode. You have your +3. Your domain of this guy, you were having like lots of negatives way too soon. You had -3. Bingo. Yeah.
It doesn't look like the bottom one going to infinity. It stops at -3.
Do you know why? Oh, and -3. Sorry, that's exactly what I was going to go do. Thank you. Guys, isn't this a limited domain, dude? So why am I actually going to show this? Is there a horizontal asymptote of 0? Yes, over here. Is there a horizontal asymptote of 0 over here? No. But why? And actually, that wouldn't even be on the axis. It's actually just a little bit below. It's a little bit below. If I plug in -3, that's going to be a 0, and then I'll still have a little baby value. But what if I plug in -4, or -5, or -6, or -7, or -8? What's wrong with... Yeah. So hence why I had to stop it and say, x has to be greater than -3. Greater than or equal to -3. The limit does not exist. All right, let's talk about some properties. We've done some more examples. Wait. Wait, can you guys check this?
I'm checking.
They tell us stuff like B and C are real numbers. Okay, they're not imaginary. That's great. N is a positive integer, so N is like a 1, 2, 3, negative. Oh, nope, not negative, positive. So 1, 2, 3, counting number, including 0. F and G, oh. Do you see how they're giving you? Okay. This is meant to help you in problems where they haven't given you a function, they haven't given you a graph. Instead, they've given you answers to limits. Instead, they've given you answers to limits. Pre-calc is doing conic sections. Which one are they on today? Hyperbolas. Okay, pre-calc is doing conic sections. They're on hyperbolas. Do you guys remember sometimes in problems they didn't give you the equation, but they gave you clues like foci and directrices or the major axis length or the asymptotes? They gave you clues, right? Instead of like the whole equation. This is kind of like that type of problem. Not that it's conic sections and not that we're dealing with parabolas or parabolas necessarily, but if they give you a limit at the beginning, it's like they're giving you clues. So instead of giving you a function, graph, or a table, they're just saying, oh, guess what? The answer to this is this. And then they're asking you to use those clues, which I like to use the word clues a lot, because it's kind of like, yeah, they could be helpful for the answer, but they're not necessarily the answer. We have to use them. And for those of you that grew up on Blue's Clues, which I guess eventually I'll have to switch to a new analogy, which will be so sad. Although, how many quality kids learning shows are there these days? Well, yeah, let's not talk about how much our society is digressing. Coming back, deteriorating, crumbling.
At least our government's not running its own people over.
That's a sign of not running its people over with tanks, so we're good. Okay. I won't come asking you for advice. Anyway, so coming back. Oh no, it came back. So distracted right now. Clues are what we need to use. Are what we need to use. Yes, that is why I do that. Now you know.
The more you know.
Clues, handy dandy notebook. Clues are used to solve answers. Some clues are helpful, and some clues, to be honest, don't really add to what we need to be doing. Some clues could be irrelevant. But if they give us limits, I bet we're supposed to use them, and this table is how to use them. Meaning, if they give you the limit as x approaches if f of x equals L, guys, if there was a scalar, if there was a constant being multiplied by that f of x, wouldn't that just be a vertical stretch or shrinkage, right? And as you vertically stretch, the cool thing is limits have this property b, because it's going to be fine. When you stretch vertically, the y's get multiplied by b. Oh, the y's! L is a y value. It's multiplied by b. What if I have something like the limit of f plus or minus g, f of x plus or minus g? Well, if I know what f's doing, and if I know what g is doing, when I put them together, as long as they are nicely behaved functions, I put limits of right now. I could, or I should probably use the snazzy word continuous, but you guys don't know the actual definition of continuous, just like kind of a description of, no breaks or jumps, I think. I can draw the graph with my pencil without pulling it up. That's a description. That's not a definition. You wouldn't go to a college class and be like, you draw it with a pencil and you can't pick it up? No. So there is a snazzy term called continuous, But we're not going to use that snazzy term. We're just going to say for really nicely behaved functions who aren't super weird with like piecewises and vertical asymptotes and jumps and all that stuff. For nicely behaved functions, we can just say, sweet, we know his limit, sweet, we know his limit, either add or subtract, whatever the operation is, and you're done. Multiplying two functions, that'd be one of those combination, well, that's a combination by addition or subtraction, a combination by multiplication or division. And it's really nice because limits say, if you know them separately, sweet, multiply. If you know them separately, sweet, divide. But the only problem with division is we still have to, whenever there's division, there's going to probably be some sort of domain restriction. Because when you divide, denominators can't be 0. So I'm going to say watch out for domain restrictions that could come about. And then if an f, let's say you know the limit as x approaches c of an f is a certain value. If it gets squared or cubed or square rooted or cubed rooted, we can actually just kind of pull out that power and say, hey, L is now going to be raised to that power. Which you might be like, this table's nasty. You don't necessarily need to memorize it. I'm not going to ask you to regurgitate the product property of limits for nicely behaved functions. But you are going to have to use it. Kyle, go ahead. Start writing the example.
Section and there's either 1 or 2 where the multiply f of x g of x and then divide.
Yeah, linear combinations. And that's where compositions came up. Compositions were the end, the hard part of that section. But the addition and subtraction were easy. Section 1.8. And that's where that funny notation came about, right? The whole like f plus g of x, and a lot of you guys, it really threw you for a loop because it was f of x plus g of x. A lot of you in the test were trying to add and then like distribute, and that was horribly awful because it was just saying the addition of f and g, both functions of x. Anyway, yeah. And that's also where the difference quotient, f of x plus h minus f of x all over h, came about, which, oh, by the way, is used to find the derivative, the slope of the tangent line. So many cool things in section 1.8. Adam.
When the A and B are together, then B just supposed to be on the other.
Oh, yeah. Whenever there are updates to Smart, sometimes my old files don't quite follow the new formatting. Yeah, lo siento, kiddos. Is that about even? Boop, boop. Okay, so what are your clues? Do you know who f's function is? Nope. Do you know what he looks like? Nope. Do you know what kind of function he is? Nope. All you know is as x is getting closer and closer to c from either side, below and above, it must match and it must be headed to 3. All you know is what's going on right around c. It's going really close to 3 somehow. From above, from below, going to 3. I'm not exactly sure how or what, but they're going to 3. What's happening to g as x gets closer and closer to c from either side? It's going to 6. And if I said fine, take the limit as x approaches c, or find the limit as x approaches c of negative 2g of x, you'd be like, I don't know who that is. But you do know this guy is going to be vertically stretched and flipped, and all the y's are going to get multiplied by negative 2. Oh, wait. It's a clue. I can just, according to the property up above, I can say the limit is going to be negative 2 times whatever the limit is of g as x approaches c. So as long as the bounds, or I should say as long as the approach matches, I can go ahead and use it and say, well, that was easy. It's just negative 12. For these, yeah. For nicely behaved functions. So what if I have f plus g? Some of you are already like, wait a minute, are we just? We are just. What are we adding? Where f is approaching and where g is approaching. If you put them together, you're going to end up with 3 plus 6 is 9. We don't mind these, do we? If x is approaching c, if f of x over g of x. So you can really? What can you really? Well, what's the limit as x approaches c of f? It's going to be 3. What's the limit as x approaches c of g? 6. So the answer really is just 1/2, and the answer is, for nicely behaved functions, yeah. Which is all that you're going to see for these types, for those of you that were wondering. Wait a minute. So how on earth do I know the final answer of this one is root 3? Square roots aren't in here. Anywhere? Good thing it wasn't someone's head. Square roots are anywhere? Oh, powers are, and square roots are really what?
Just half power.
Just powers. Good. So we can go ahead and change this to be the limit as x approaches c of f of x to the 1/2 power. So I can say 1/2 power 3. Dun, 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 dun. Are we okay? Do we mind these, Robbie? Do we mind these? You do? So, you know how I was saying well-behaved? Guess what well-behaved functions are? Can I show you? Basically? Remember how, just real quick before we go to that page, remember how when we were finding limits, they were kind of, I mean, the piecewise threw extra difficulty in, but they were kind of two different situations, right? Let's say the limit as x approaches c of f of x is what we're trying to model here, okay? There were kind of two different cases, true? For one, x had to, well, who am I approaching this time? I think we used a before. Now it's a c. Either way, x is approaching c, right? For this whole portion of the graph, x is approaching c from below, which means a little minus, right? And for this whole portion of the graph, which is being shown in a table, x is approaching c from above, which is a little baby plus, right? So x is approaching, trying to see what y is approaching. I did something to the effect of this one can be like L from below, and I'm going to name it L1. And this one could be a limit also, L2, and sometimes they match. And if they match, they exist. So our question that we're asking, does L1 match L2, right? Isn't that our big question as we're coming from below and above? Does this limit match that limit? Right? Do your shoes match? Do the limits match? But let's say they do match. If so, the limit as x approaches c of f of x is whatever that matched limit is. If L1 equals L2, then it's okay, fine, cool. The limit exists, the limit is that number. If not, what would we say? What if they don't match? The limit is not, why is there, go away. The limit does not exist, right? If they match, cool, that's the limit. If they don't match, okay, well, cool, but DNE. DNE. But do you guys realize there were two different cases, even if so? So I can say that if so, aka the answer was yes to the matching question. Do you remember how either it could be there or it could not be there, right? Either this could be mimicked in the table or it could not be mimicked in the table. Guess what? These ones, nicely behaved. Oh, sweet, where I'm going is right there. Wait, so if nicely behaved ones always have this right there, do we have to do this, or could we just go right there? If nicely behaved functions, limits will be exactly what happens when you plug in c. Well, couldn't it be a shortcut to get this by just plugging in at the very beginning? See? Some of you were kind of doing it yesterday until you got to where it was error and you're like, And I was like, it's not the at, because it wasn't the at. But is it sometimes for nicely behaved, the at? Yes. So for nicely behaved, if the limit is going to be the guy that these guys are approaching, we'll this stuff. Done. So what are we doing right now? Nicely behaved, or well-behaved, fine. Well-behaved functions, check it. The limit as x goes to c of f of x is equal to f of c. All we have to do is substitute. Snazzy way of saying substitute. Plug it in, plug it in. to show you the next page really quickly. Some of you might get scared. Don't worry, I'm coming back. The next page says we're going to solve 6 limits in 3 minutes? No, we've only done like 2 today, maybe 3. How are we going to do 6 limits in 3 minutes? Actually, probably 2 minutes by the time some of you finish writing. Uh-oh, we're losing our time. Don't worry, I have no anxiety or stress. We're going to bust them out. Why? We just said if it's a nicely behaved function, we don't have to do all this making it match, coming from either side, using a table or a graph. We can just say, ha-ha, what are you? So guess what? Ha-ha, what are you? Well-behaved functions, polynomials, rationals, everywhere, except at the discontinuities. Exponentials, trig functions, except at their vertical asymptotes. Basically, if you plug in and it works, you're good, unless he's a piecewise or he's at a discontinuity, a domain problem, which means, how on earth do I take the limit as x goes to 4 of x squared? X squared is a polynomial, so all I have to do is plug in 4 and say, oh, it's nicely behaved. 16 is where it's headed and where it's at. How about 5x? Oh, he's a polynomial. I mean, he's a line, but whatever. He's nicely behaved, so I can just plug in and say, oh, hey, he's headed to where he's at, 20. Tan of x over x. Oh, my goodness. Tangent has vertical asymptotes at pi over 2, but not at pi. Tangent's just fine at pi. So I can just plug in tangent of pi all over pi, and guess what tangent of pi is? Tangent of 180. Tangent of pi. Yeah. 0 over pi is 0. Oh my goodness, square root of x. He's not nicely behaved for negatives, but is this a negative? Oh, well, fine. So therefore, he's nicely behaved at 9. Therefore, he's going to be 3. Tangent of, not tangent, sorry. The limit as x goes to pi of cosine's not nicely. Oh, yeah, he is. He has no brakes. He has no jumps. He's just a happy little wave doing his thing. Can't I plug in and say, hi, nicely behaved people. Let me plug in cosine of pi is equal to -1. No. Cosine?
By no means.
1, -1, +1. Cosine of pi is -1. Negative pi. And he's basically a polynomial after you FOIL him out. He's just a quadratic. He's nicely behaved. So therefore, I get 3 plus 4 squared is equal to 7 squared is 49. 6 limits in less than 2 minutes. How? Nicely behaved. Guess what section 12.2 is? Not nicely behaved without a calculator. Ooh, it'll be fun. But this section, you're using your calculators for tables, for graphs, of some nicely behaved, some not nicely behaved, and then you get to end with plug and chug of the nice ones. Bye, guys. Have fun with limits. You're welcome. Wish the pre-cal kids good luck on hyperbolas.